In this video, we're going to lay the background for some of the math that we'll do when we're talking about phase changes, and then we're also going to look at some phase diagrams. So to begin with, this is a great chart that kind of explains what happens to a substance when you add heat to it. So this specific example is that of water. And so at each stage, you still have H2O, but the water is in different forms. And so it starts out as ice, where you've got a very rigid structure. You have a lot of really strong intermolecular forces because they're all, locked in place by the structure of ice. And then in the blue, step 2, that's where you're transitioning between the ice, the solid phase, and the water phase. Both ice and water are present, but you're slowly losing those connections between the solid rigid particles, and you're turning into water where the substance can flow freely. And then the next step is water. Water is heating up, it's increasing its temperature, and then it starts to turn into steam. And so at step 4 now, we have both a mixture of water and steam. And so your sample is boiling at that point. That's your boiling point. And then the last step, of course, is steam, where those intermolecular forces are really losing their grip because, those water molecules are moving around like crazy and they don't have time to interact and their spacing is greater. So at each step, those intermolecular forces are going to have a very large role, but it's just then what's happening. How are we going to describe those changes can be described mathematically. And so we're going to do a little bit of both in that class. In this class, we're going to discuss both the concepts between what's the difference in the intermolecular forces for ice, water, and steam, and then also how does the strength change as you apply energy to the system. So we're going to practice drawing some of those diagrams in future videos. In this diagram, I want you to see this picture of where you place a liquid into an Erlenmeyer flask and you place a stopcock on. The very first thing that starts happening is the liquid is going to start to evaporate. Why does it evaporate? Well, if there are no water molecules, let's say this is water, then it's going to start to evaporate because it wants there to be this an equilibrium established, where the water molecules in the solution said, hey, there's none in the gas phase above me. How about I evaporate? But then some of them are going to collide with walls, some are going to recollide with the surface of the water, and so they're going to go back into solution. So that's condensation. So at any given moment for this capped flask, you're going to have both evaporation and condensation happening. Initially, you're going to have a really high rate of evaporation, but then that's going to flatline, and then your rate of condensation is going to increase, like you see in this figure on the right, until the rates of the two are equal and equilibrium vapor pressure has been obtained. And so when we talk about vapor pressure, we're talking about the relationship between those molecules in the gas phase and the liquid phase. And so there's some ideal pressure at any given temperature which allows for those two rates to be equal. So your equilibrium is achieved when your rate of evaporation equals your rate of condensation. What that means in terms of physical movement of molecules is that the number of molecules out of solution, the number of molecules in solution are going to pretty well stay steady with time, because anytime a molecule enters solution, another one pops out. That's your condensation and then your evaporation. And so when we're talking about vapor pressures like we're going to be doing, we're talking about condensation, evaporation, you should be picturing processes like this, where there's an equilibrium stasis that is set up between the substances. If you just see a liquid sitting on the counter, note that that liquid is not stationary. Some of it's evaporating off, and if it's closed, some of it's probably recondensing. All right, there's lots going on that we just can't see with our naked eye. So then you might have a figure like this. What is going on here? Well, the vapor pressure of the liquid is shown by the green curve, and the vapor pressure of the solid is the orange curve. And so what's happening is whichever vapor pressure is lower is the state at which water is going to exist in. Meaning, look at the temperature column. So temperature here is 0 degrees in the middle. And what do we know about 0 degrees water? That's its freezing point. So below temperatures of 0, we are going to have a solid. Greater than that, we're going to have a liquid at most pressures. Not all, but most, okay? And so when we're looking at this, why does that happen? while my vapor pressure for a solid is less than. And remember, substances are just like us. If they can relax, they will. So they'll take the lower energy state. And so the lower energy state is that of a solid, meaning for water to exist as a solid, it takes less energy than for it to exist as a liquid at temperatures below zero. Then at temperatures above, notice how the two lines invert. And now the vapor pressure of the solid is higher than the vapor pressure of the liquid. And so now at temperatures greater than zero, it's going to be more energy favorable to exist as a liquid. And so this vapor pressure is one of these many different properties of ice that allows us to think through conceptually, why is water a solid at temperatures less than zero and greater at temperatures more than zero? And so vapor pressure is exactly what we were just looking at here. This idea of you've got some gas molecules here above the liquid and you've got an equilibrium established. And so if you've got vapor pressure of a liquid, that's exactly what we're looking at here. And the vapor pressure of the solid is similarly. Are those molecules going to want to stay in the solid phase? Or are they going to want to go into the gas phase? And so a way we can look at this is as long as the vapor pressure of the solid is less than the vapor pressure of the liquid, it's easier to remain in the solid form. And if it's greater than that, it's easier to remain in the liquid form. And so these different molecules, whether it be water or anything else, it's going to always choose the easier route, because these molecules, if they're going to evaporate, which is your vapor pressure, right? If they're going to evaporate, they're going to want to turn into a gas. And so in order for them to stay as a liquid or stay as a solid, they need a low vapor pressure. That way those molecules stay in that state instead of escaping and becoming a gas. And so just note from this that the vapor pressure of the substance is going to determine the phase or the state of that substance. So a question similar to this is, how do intermolecular forces relate to this figure? Oh, so much, okay? Meaning, remember, think about the way intermolecular forces differ for a solid to a liquid. They're held more rigidly, so they're stronger in a solid and less in a liquid. Well, pressure is related to all of it. Whereas you add temperature, you add energy. Whenever you pressurize a sample, you're condensing it, you're pushing them all together, which means you're forcing those liquid molecules, for instance, to have stronger intermolecular forces. But the vapor pressure of that liquid is still higher at temperatures less than zero and greater at temperatures more than zero. And so it's those forces between them that are going to determine the pressure at which the liquid or the solid is going to turn into a gas. So how do they relate? They determine the properties of the liquid or the solid, and those properties determine the vapor pressure. And so you could play out and tweeze out all the little nuances of it, but that's kind of the big picture. Now here's a chart of vapor pressure of water as a function of temperature. So notice at low temperatures of zero, you have a low pressure. As you get closer and closer to boiling point now, your pressure is increasing. And so as you're increasing your temperature and you're increasing your internal pressure, which means as you're getting to be a higher and higher pressure internally, you're more likely to turn into a vapor. So think back at this figure. See how the vapor pressure of the liquid is increasing from 0 to +5? That's because it's getting more and more likely it's going to shoot up and boil off, okay? And so that's what's happening here. Your pressure is increasing as you're increasing your temperature. Once the internal pressure equals the pressure around the substance, that's when the substance is going to boil. Remember, your force equals mass times your acceleration. Your pressure is force per area. And so all of these have to do with those intermolecular forces, because you're forcing how much are you pressurizing a given substance based on the surface area. So if you expand the surface area, stuff's going to evaporate off faster, but that's a rate. That's not the vapor pressure. The vapor pressure is internal. So let me say what I said a moment ago again. As you increase temperature, you're increasing the internal pressure. Once your internal pressure equals your external pressure, that's when you're going to start to have evaporation. Your substance is now going to turn into a gas from the liquid phase. And that's why your boiling point actually varies at different locations depending on where you are. And so when you're up high on like Mount Everest or Mount McKinley in Alaska, your pressure is going to be a lot lower because you don't have a lot of atmospheric particles pressing down on you. You're higher up above sea level, so your pressure is lower. So your boiling point goes down. Because remember, if your vapor pressure is at 70 degrees, 233, at that point, you're equal to the pressure around you if you happen to be on Mount Everest. And so that's why as you increase to sea level, you increase your feet above sea level, you're going to decrease the pressure around you, which actually decreases your boiling point. And so this little part down here, substances boil when their internal pressure equals the external pressure. And so we consider 100 degrees to be the normal boiling point simply because that's approximately the sea level. So we just have defined 100 degrees to be normal because at sea level it's defined as 760 torr or 100 degrees. All right, now you might ask, okay, what's the relationship then between this vapor pressure and temperature? And that's this Clausius-Clapeyron equation. The first equation you see is the relationship if you were to plot it as y, where y is equal to ln of vapor, your vapor pressure, and then your x is 1 over temperature. If you plot those two against each other, you would have an equation y equals mx plus b, where your slope is your vapor pressure divided by the gas constant, and your b, your intercept, is some random constant. But that's not as useful because typically in lecture we're not plotting the data. That's a great equation for lab. And so typically in lecture we'll have this second equation where we're comparing two different states, one temperature compared to another temperature, and comparing the vapor pressure across those two temperatures. And so you end up with this equation. And we've got a video that shows an example of how to utilize the Clausius-Clapeyron equation. So to kind of summarize a lot of these phase diagrams, just note that your vapor pressure is related to temperature. As you increase that internal pressure, you're getting closer to your boiling point because once the internal pressure equals the outside temperature, your sample is going to turn into a gas.